Okay, so this is Rain Pigarin. This is for CU Boulder's ASEN 1969 class. We were supposed to kind of work about 5 hours or less on a project that I guess just represented our abilities or interests in a way on a space-related topic. So what I did is I used, I'll explain it a bit later, but I used a software called KSP RSS to work a little bit on simulating a manned mission to Callisto, so taking 3 astronauts to a moon around Jupiter and returning them safely. I didn't get all the development one done that I wanted to in those 5 hours, but I did make a lot of progress, and I'm interested to show you guys what I got. Yep. Alright, so what is KSP? So KSP is the acronym for a game called Kerbal Space Program. You shoot rockets off. It's kind of a semi-realistic space exploration game, so it considers everything from the physics of bodies to the physics of propulsion systems to I don't know, aerodynamics to all sorts of different things. It's I guess one of the most realistic space games in terms of you can build whatever you want and then you can just try and see what happens. Uh, anyway, you can build space stations, you can make your own space shuttles, that kind of thing. You can go and land on their analog for the moon because they don't make the game based in our solar system. Sky's the limit, really. You can go to other planets and come back, all that kind of stuff. My favorite game, if that isn't obvious. And KSP RSS. RSS is an acronym standing for Real Solar System. It's a mod pack. It's a heavy mod pack that overhauls the Kerbal Space Program game so that everything from the aerodynamics to thermal properties to structural properties to what planets are in the solar system, what their distances and velocities and tilts are. It's a bunch of nerds that got together and really wanted to try and turn Kerbal Space Program into something uh, a lot closer to simulating our real solar system. And it's actually interesting because it's accurate enough to the point where you can kind of use it, at least from like a math and engineering perspective, to help inform what a real mission might look like and why. So everything from the masses to the thermal properties, all that kind of stuff. It's a good tool for simulating that kind of thing and seeing what it would look like. It's like, well, if we took people to Mars, what would the vehicles need to look like? How much would they need to weigh? So on. So that's kind of why I chose to use it for this manned mission to Callisto. Just running through a few relevant laws and principles. Newton's first law basically says that if an object's in motion, it'll stay in motion. If an object's at rest, it'll stay at rest. And how that's relevant to this project is if, for example, like you shoot off a spacecraft, if you use a rocket to push it away from an Earth orbit or something like that at 4,000 meters per second, right? Maybe that would be roughly 12,000 feet per second. That's a ridiculous speed. And in space, there's much, much, much less air or particles or something for it to interact with. So the principle goes, like, despite the fact that it's shooting by at, like, 12,000 feet per second or whatever that is, there's not going to be, like, air friction or any other random forces, anything except gravity that's going to slow it down, essentially. So it'll keep going like that for years and years and years, and then its trajectory is only going to be altered by the gravity of objects like Earth or the Moon or other planets, but especially the Sun. Going through these more quickly. So Newton's second law, it can be just characterized as the equation F equals ma. All that basically saying, like, if you know how much an object's mass is, and you know how much force is being applied to it externally, like forces that don't net out just by the object by itself, then you can figure out what the acceleration of that object is. And then, working backwards, you can figure out the mass if you know the force and acceleration, or you can figure out the force if you know the mass and acceleration. The reason this is relevant to my project is this is what's used to determine how much acceleration is produced by the little electric engines that run this spacecraft. We know the force produced by them when you provide them with enough power. We know the mass of the full vehicle, so you can figure out the acceleration of the whole rig from that. All right, now Newton's third law, for every action there's an equal and opposite reaction. So all that means is when the electric propulsion system grabs, it runs on xenon gas. It's a heavy, mostly inert, completely inert gas that's polarized, accelerated electromagnetically or something like that, and then shot out the back at some ridiculous speed. And it's basically just saying that for every action, there's an equal and opposite reaction. So when you throw the gas at the end at like a ridiculous speed, then it'll slightly push your spacecraft forward. Gravitational force equation. So this one talks a little bit about the principle of the closer you get to an object, the more its gravitational force will interact with you. And then, of course, going back over to here, that force matters because it'll correspond to the acceleration of the craft. Yep. Let's see. Inverse square law. So this is kind of the technical explanation of why moving a little bit further out from the sun means you're drastically reducing the amount of power that you get. The principle is the energy twice as far from the source, being the sun, is spread out 4 times the area, so it's 1/4 of the intensity. And Jupiter, of course, I don't remember off the top of my head how many astronomical units it is away from Earth, but it's multiple times further away from the sun than Earth is. So that becomes compounded, and then you're looking at maybe, I don't know, 3 to 1%, I'd have to check the numbers, of solar power from the sun. So that's why this thing isn't powered by solar panels, because way out at Jupiter, there wouldn't be enough power from the sun. All right, the ideal rocket equation. This one's pretty important, but essentially what you want to get out of it is that the velocity, the delta V, that's a term I'm going to use, it's kind of like, you can imagine it like the range on your car, right? So if you fill up your fuel tank all the way up, you know, your car weighs some amount, you're able to go 200 miles on a full tank. So the delta V is kind of similar to that. It's your budget for how far you can go and what you can achieve in space. There's a bunch of kind of complicated ways to work with it and to figure it out and to think about it, but long story short, you want to think of it like a budget. There's some sort of minimum budget that you need in order to do some kind of task or accomplish some goal, like leaving a low Earth orbit, going to Callisto, burning to go into a low orbit around Callisto, and then returning. And this equation says that delta V, which is in units of velocity, so meters per second is what we usually use, is equal to the exhaust velocity, which then breaks apart into the gravitational constant times the specific impulse in seconds, which we'll get into later, times the natural log function of, it's called the mass fraction. So the mass fraction is how much your spacecraft weighs when it's fully fueled, divided by how much it weighs when it's fully empty. And that little graph there in the middle is just meant to represent how tyrannical this equation is, in that, like, the more you want to accomplish, the exponentially more fuel you have to carry. You want to scope up your mission a little bit, or you want to make your spacecraft weigh just a little bit more, and there's going to be an unfair and disproportionately large penalty for that in terms of how much fuel you need. Yeah. All right, and specific impulse. So you can think of that kind of like the miles per gallon on your vehicle. So the better it is, maybe with like a Toyota as opposed to like an old Ford truck or something like that. There's much more going on behind the scenes and much more that plays into that. But long story short, the better your specific impulse, the better your miles per gallon. So for a mission like this, where you're doing something difficult that requires a lot of velocity change, that requires a lot of delta V, you're going to want as efficient of a system as possible. So you can see from this graph, like the stuff lower down might give you better thrust, like a chemical-based propulsion system, maybe the kind of stuff that the space shuttle um, vehicle launched on, or SpaceX's rockets. Um, what we really need for this mission is an electric propulsion system. I looked at nuclear thermal, but it wasn't possible because the penalty was too great for going with a little bit of a lower efficiency. Um, yeah, and a trend you can see, just as a fun aside, is basically like um, as your thrust increases, usually your efficiency decreases, and as your thrust decreases, your specific impulse increases. So all that to say, like, you have to make a trade-off. Do you want a high thrust system, or do you want an efficient system? And in this case, we went with an efficient one, but the penalty is that the entire thing basically produces a half Newton of thrust, despite the fact that it weighs. I'd have to look at exactly how much it weighs. Let's check that out real quick. I'm curious. Yeah, so this whole thing weighs 536 metric tons. Wow, that's pretty heavy. Okay. Hohmann transfer. So this is just kind of a principle to say if you want to change going from one orbit to another, it doesn't have to just be a closer orbit going to a further orbit, that kind of thing. It can be more complicated too, but I don't want to get into that right now. You perform two burns. One of them is an intermediate transfer orbit that gets you from one target to another, and then the other one is you kind of catching up or matching the speed that you want at your final orbit. In this case, you're just kind of trying to go from a circular orbit to a circular orbit. There's not like a target or anything. There's not maybe a space station that you want to dock to and meet up with, or a planet or a moon that you want to match speeds with to eventually land on or something. But that's how the principle is applied in this case. And in this case, like the Hohmann transfer, that I guess the main one that's going on is, going from being an object around Earth's orbit around the sun to being an object, matching up with Jupiter in its orbit around the sun. So instead of the Earth in this image, that would be the sun. That initial orbit would be around Earth. The final orbit would be around Jupiter. Again, we'll get into that a little bit more. Yeah, so this, I used the NASA trajectory browser to just figure out about what it would look like for this mission to happen in terms of like real trajectories, real orbits. I did a lot of work just kind of fine-tuning what's best for this mission, when it would launch, all that kind of stuff, but I ran out of time before it became really significant. Yeah, but all that to say, essentially what would be going on here is you'd launch sometime around 2031, 2032 into this orbit around the sun. There would be kind of a deep space maneuver to change the orbit at that X. And then over here, it would like re-encounter the Earth. And I didn't really plan this in my slides, but I should have talked about a gravitational slingshot where you trade off energy between a planet and a spacecraft. And by flinging yourself by and close to a large body like a planet or a moon, you actually gain speed without using any fuel. So that's what would be going on at that next intercept. And then its new trajectory would be this one that goes further out all the way until it encounters Jupiter. At Jupiter, you would do a burn, just like the Hohmann transfer earlier, to catch up to Jupiter. During this section here in the flight, that would be when around Jupiter, you make an encounter with Callisto, you do some complicated work to orbit it, and then, the lander breaks off, lands on the surface, launches itself into orbit around Callisto, and then re-encounters the mothercraft. And then from there, whenever the mission's done, then it would burn to leave Jupiter and then just come back to Earth. I kind of chose the trajectory in a manner where the re-entry velocity back at Earth would be low, lower than some other potential trajectories, some other missions. And I did that because, the slower you re-enter, the less ballast of a heat shield you would need for some kind of capsule re-entering, that kind of thing. Yeah. Okay, so I'm sorry for the quality of this image. I couldn't really find much better, but another interesting thing to note is that there are things called spheres of influence, where basically you can draw an imaginary sphere around any object, and based on all kinds of complicated things like how massive the object is, how close the most powerful nearby body is that also has gravity, you can figure out in about what sphere or in what radius or how far away like the big player in the gravitational forces on your spacecraft, um, English, is going to be. Anyway, rather than doing a bunch of complicated math to figure out how the spacecraft is going to be influenced by the gravity of, if you're around Callisto, then say like Callisto and Jupiter and the Sun, you can say like once you're close enough to Callisto that the effect of the gravity on from Jupiter and from the Sun is going to be more negligible, and you can just do the math and simulate it based on Callisto acting on it, and that's way easier. The Oberth effect. So this, I don't want to get into it too much, but because of weird physics, when you get closer to an object of significant mass, so like the Earth or the Moon or Jupiter or whatever, you can use that to get a more significant change in your velocity. So another kind of way to save delta V is you get really close to an object when you do your burns if possible. Electric propulsion systems. Yeah, I've kind of already briefly talked about that, but as the technology stands right now, it produces a ridiculously low amount of thrust. The N-Star one that I used, which has been tested and used for a lot of different missions, produces like 1/10 of a newton of thrust, which is really tiny, and it uses 2,300 watts of power. Which is a little ridiculous, that much power for that little thrust. But the trade-off, like I was saying earlier, is that efficiency. You need way less fuel than you would ever need for a chemical propulsion system because of that. And for that reason, it facilitates certain kinds of missions. One use of it is one of these engines was able to help the Dawn spacecraft visit Ceres, which required, I don't remember the numbers, somewhere between 8 and 15 kilometers per second of delta V, so quite a lot. Okay, Earth reentry velocity. Kind of talked about that. We want to minimize it as much as possible. Okay, spacecraft life support. I did a little bit of math behind this because I'd done it before with the previous project, but basically when you have a crew, when you have people on board, your considerations go through the roof. You have to consider a whole suite of other variables in your engineering, but you can kind of summarize it in 4 pieces for the main in terms of like a class of things called consumables, which means like, not just a piece of equipment you would need to put on board one time for a whole 9-year mission, but, stuff that you're going to use that can't be reclaimed, that kind of thing. So the main consideration that I was trying to piece in here was just the mass of how many consumables would be used. And those consumables mainly are food, water, oxygen, and then you also have to have lithium dioxide in order to kind of scrub carbon dioxide from the atmosphere inside of your spacecraft. And this I'll talk a little bit more about later. Okay, this project and so this is kind of a subway map that you can use. It's a tool that helps relieve the complications of the considerations of like how much delta V you need to get from one place to another. You can kind of follow it along like a subway map, add up the numbers, and figure out how much delta V in meters per second you need total to do something. So this is what I used eventually to get just a rough estimation of how much delta V would be needed to perform this mission. Okay, and here's our specific flight plan. I'm going to need to kick it. There we go. Now that's full screen again. Let's see. Oh, cool. You can still see the cursor in this mode. So I'm going to say you can pause here if you want to look at more of the numbers behind this, but I'm kind of on a time restraint. So this was the math I did to get how much food you would need. Again, you pause here if you want to see. The math on the water, the math on the oxygen that's consumed, and the math on the carbon dioxide filtration system. Although I wasn't really too sure about this one. There might be a more mass efficient way to reclaim and reuse that, like you use a little bit of power on lithium dioxide and break it apart again or something. I just don't know. But this is what I did just to kind of at least say it would be necessary. So let's try and accommodate the mass needed for carbon dioxide filtration. That's what you end up needing total. I kind of made a guess saying there would be 3 tons of equipment too. So the actual hardware that would be reclaiming the water, reclaiming the air, cooking the food, blah, blah, blah. Yeah, so I added a factor of safety. I guess I should mention I added a factor of safety for all the consumables too, food, water, oxygen, all that. I just kind of went with a 10% factor of safety just for fun. And long story short, what I ended up with is that you need just under 26,000 meters per second of delta V, which is, you know, about 26 kilometers per second. Okay. Sorry, this is getting kind of rushed near the end because I'm coming up close to my submission deadline. But you use the ideal rocket equation and you figure out the mass ratio that's needed given the efficiency of that electric propulsion system I said we're using and the delta V that we need. You get a mass ratio of about 2.34. That means that when the spacecraft is fully fueled, it weighs over twice that of when it's empty, when it's exhausted of fuel. And that's what I ended up using later on to figure out how many fuel tanks are needed for this vehicle to have all the delta V it needs. So the electric propulsion system, I said that a nuclear reactor, a nuclear fission reactor cluster powers this thing. Each of those nuclear reactors that kind of existed as a stock part produced 4.5 kilowatts. Each of those engines needed 2.3 kilowatts. So I ended up going with 3 nuclear reactors powering a cluster of 6 of those ion engines altogether. And long story short, you end up getting just a little over half a Newton of thrust for this whole thing, which back of the envelope calculation means, let's see, F equals MA. Oh, this is bad. Okay. So that means that the acceleration that you get when you first start flying the spacecraft is about 1 times 10 to the negative 6th meters per second squared. Oh man. Anyway. Yep. Yeah, the math works in some ways and it doesn't in other ways. That probably would be insufficient acceleration for the mission, even over, you know, however much time. Usually with electric propulsion systems, you burn them for days and days on end, but that's the one very, very weak spot of this mission right now. Is there would need to be some perfect, wonderful engine that produces way more thrust for far less power for this to work. Yeah. Let's see, is that the end of the slides? Yep. All right. Alright, so I'm just going to give you a little bit of an overview of this spacecraft. Not going to get too much into the numbers because got a little low on time, but I'll try and give an overview of the basics. So this area here, from the top up to right about there, that section is the manned quarters. So on the middle there is supposed to be a laboratory. On the top would be a capsule. Whether or not I would try and design it so that that would be the actual re-entry capsule post-mission or not, I'm not sure, or if I'd design something else for it. That right there is actually the main living quarters. We'll be able to see inside it later on. I'll try and zoom in a little more so it's a bit easier to see. At the top there is meant to be sort of a NASA standard docking system. That would be where the lander that actually took the 3 astronauts to land on Callisto would decouple, go down, and then return. I didn't have time to make that within my time restraint, so for now I just put in a ballast to account for about 10 tons or 10,000 kilograms for the mass of that lander in these 4 black ballast tanks at the bottom there. And also considered in those ballast tanks are the mass for all the life support stuff that you see in the PowerPoint. Let's see, so we were up at the top with the manned quarters, and here I was kind of trying to put together a little bit of a system to represent some science equipment that the astronauts would be using throughout the duration of the trip. I just kind of threw some stuff on, but what I came up with was a radar altimeter. There was kind of a multispectral sensor there. That's just kind of breaking the meta. That's a system in the game that lets you control the spacecraft easier. I have some various sensors on here, everything from a biological experiment to a Geiger counter to a thermometer, a micrometeorite detector, which I realized I'd probably want to have mounted more near the front on the exterior, so it was actually exposed to potential micrometeorites. Anyway, seismic accelerometer, orbital perturbation experiment, barometer. Anyway, some of these experiments would be useful in this scenario where it's orbiting around the environment of either Jupiter or Callisto, or it's in the interplanetary space. Some of them wouldn't. Honestly, I just kind of wanted to throw something in to represent the mass of potential instruments. This is a cargo base, so, you know, I wanted to kind of compensate for the mass of a closed system that might be necessary to protect some instruments. When I was running some tests earlier, I noticed that the communications dish was weak enough or thermally vulnerable enough that when it encountered Jupiter, when it came close by to it in the orbit, the radiation was harmful enough to it that they actually failed. So that might be the example of something that would eventually go inside of the cargo bay to be protected during a few parts of flight. I think it would be okay to lose communication for certain critical parts of flight where it's in a dangerous environment for instruments, just because, you know, you have it manned, it's not unmanned, so the astronauts can take control and have control of the craft even if you don't have a signal back to Earth at some points in the mission. So continuing on, that's kind of a small tank meant to represent the mass of RCS systems, or reaction control systems. So the reaction wheels here, I put about 5 of them on board or something. They use very rapidly spinning disks to reorient the craft without using any fuel, but those can, what's the term? Those can become saturated, where essentially the wheels are spinning so fast that you can't spin them up any further, or, you know, you have to de-spin them in order to allow them to continue to work. It's a little complicated, but in order to undo it, you can have sort of these little thrusters oriented radially around the craft. You burn a little bit of fuel, and then you spin down the wheels so they can get back to working again. So that was mass meant to compensate for that. The engines themselves, I didn't have time to throw in. the positions and such. But you can imagine like the Apollo Command and Service Module, those RCS block engines, it'd be something similar to that, oriented and placed in good places around the spacecraft. Anyway, continuing on more interesting parts, these are 3 stacked nuclear reactors. They work with uranium. Each one produces 4.5 kilowatts of power. These are some massive radiators I wanted to put around in a 6x symmetry to reject all the heat generated by these 3 reactors. And the reason that so much power needs to be generated, and also why it can't be solar power that's working for the spacecraft, is it's running some very high power electric propulsion engines, some ion engines back here. Each one of those is really greedy. It needs about 2.3 kilowatts of power per engine. And you can't just use massive solar arrays, although that might be better mass-wise, because, you know, inverse square law, the spacecraft's very far from the sun, so there wouldn't be enough solar power like on around Earth to run anything significant. So power generated, these tanks here, there ended up being 24 of them total, each one holding about 13.5 metric tons of xenon gas, which is what runs those ion engines, that electric propulsion system. That's, you know, using the ideal rocket equation, that ended up being about what's necessary to achieve that delta V that we needed of, it was just under 26,000 meters per second. But the way the game works, you can't have part of a tank. So it just ended up being quantized, so we have a little bit more delta V than that. Yeah. Yep. Those communication dishes are meant to be relay dishes, so that the lander itself would communicate back to the mothercraft and then the mothercraft back to Earth, as opposed to having to have a sufficient communication system on the lander itself to communicate all the way back to Earth. Although there is kind of a historical precedent for that kind of thing working, with the Cassini, how do you say it, Huygens mission or something like that, where there was a little lander craft that made it to the surface of Titan, and they ended up having to communicate directly with that little lander spacecraft to Earth, because of some kind of communications failure where it couldn't bounce off the relay of Cassini, the mothercraft. Anyway, if that could be wrong, that's just my memory of it. So this is, yeah, that's the craft. Let's throw it in simulation mode and just to see what it would look like if I could do this whole mission. Let's put it around Callisto. Let's see if this will work. I have a few tricks up my sleeve if this doesn't work first time around, but I don't know. I figured all the hours I put into the project, it'd be really nice to at least see it around the target moon. If it isn't clear, I like Callisto. I may have a difficult time defending why, but alright. There we go. Cool. I'm actually kind of surprised that worked first time around. Let's see. That's interesting. For some reason the velocities are wrong on this. I'm not quite sure why. Simulation setup in progress. Okay, I think I see. Well, that's an easy fix if this works. Set orbit. Callisto, centimeter axis. Let's put it a little further out. Okay, there we go. It's trying to override it with the simulation setup. I wonder. trying to get to the day side, so it's easier to see Callisto, the surface. Anyway, this is kind of the map editor portion of the game. So usually you would see your orbits in relation to other orbits and all the bodies. So there's Callisto. There's about the orbital height we'd be at. Normally there'd be a circle around it to represent the orbit. KSP RSS, or the real solar system overhaul, is a little bit janky in places. For example, the angles of the moons relative to it. Anyway, the whole solar system, I know this is odd, but it's offset, or it's tilted by about 24 degrees. I think that had something to do with trying to correct for the Earth's tilt or something, and then the devs of the mod messed up in a couple places or something. But everything else in terms of like the masses, the velocities, all that kind of stuff, the positions, all of those are correct for real solar system. I just kind of wanted to take a sec to look at Jupiter since I got unlucky, and we saw the back of it from the point of view of the spacecraft. If this was working right, I could also kind of warp time to be able to get to a different point in Callisto's orbit around Jupiter. Yeah, so that's what the spacecraft looks like. I'll just kind of back out of a lot of stuff here to get a view, I suppose. So that's what the spacecraft looks like above the surface of Callisto by a good 111 kilometers or so. That's sea level to Callisto, so the actual distance to the ground would be different. Here's a point of view from inside the spacecraft. So that's the capsule. I'll switch to this one. It's kind of the interior. All right.